Welcome to another edition of Coonrod's Corner, brought to you by the Rogers Corporation. Today's topic: how does PCB fabrication affect RF performance? Now here's your host, John Coonrod.
Hello, my name is John Coonrod with Rogers Corporation. I am a technical marketing manager. Today I'm going to be talking about how PCB fabrication can affect RF performance. Now there's many different normal variations that happen in several of the processes in making a circuit, and some of these can have an impact on RF performance, and the RF designer should be aware of these, and they should also talk to the circuit fabricator to understand what the range is of these normal variations, and then try to simulate these variations in their RF simulations and modeling to really get a more consistent performance out of their circuit when it's built in higher volume. Now, as I said, this is a very big topic. There's a lot to it, and there's much more information that you can get on our Rogers Technology Support Hub, and at the end of this video there will be a URL there to send you to that website. So with that, let's go ahead and get started. Shown here are 4 different RF structures that are commonly used in microwave and millimeter wave applications. Now I'm going to be talking on this slide and the next many slides and graphics about millimeter wave, and the reason why is because millimeter wave with the smaller wavelengths are much more sensitive to any kind of anomalies. So the concerns that I mentioned about millimeter wave also apply to microwave, lower frequency, but usually less problematic. So a worst case scenario is really talking about these variations in the sense of millimeter wave. And also along with that, there are many more new applications every day with millimeter wave, and that looks like that's going to be continuing for years to come. So the 4 different structures I'm showing here is microstrip, grounded coplanar waveguide, strip line, and SIW, which is substrate integrated waveguide. And I'm given a rather subjective rating here of how much the RF performance of each of these structures can be affected by normal variations of the material itself or of circuit fabrication, or actually both. So in the case of microstrip, I show that there is a minor influence, and what I mean by that is microstrip, the RF performance of microstrip has is adjusted in a very minor way to circuit fabrication variables. So circuit fabrication does affect the RF performance for microstrip, but in a pretty minor way. Grounded coplanar waveguide, that depends on the design and the frequency, but it's typically moderate to significant. And I'll talk about that much more as we move along here. Strip line, that also depends on the design, and it could be moderate or even minor, depending again on the configuration and the design of the circuit itself. And then SIW, that is significant in most cases at lower frequencies. That could be more a moderate rating. Now, to become a little more familiar with the concerns, the next graphic will talk about these same issues and give a little more detail. Shown here are the same 4 RF structures: microstrip on the left, grounded coplanar waveguide, strip line, and SIW to the right. And here I'm also given a subjective rating of the different variables that can impact RF performance. So in the case of microstrip, the number 1 influence that can affect RF performance is conductor width. And then the next one of the most significance would be the substrate thickness. And I'm talking about tolerances here. So the conductor width is not going to be perfect on every circuit that is made. There is some tolerance of plus or minus something. And that's really what I'm talking about, the variation that's a normal variation. And same with the substrate thickness. There is a thickness tolerance. So for microstrip, these different issues listed here are listed in order of significance, but also you got to remember that microstrip is not heavily impacted. The RF performance of microstrip is not heavily impacted by these influences. However, in the case of grounded coplanar waveguide to the right of that, there's a longer list of influences that can impact RF performance due to circuit fabrication or material variations, and in this case they are pretty significant. So the first 3, conductor width, conductor spacing, and the copper thickness are really the biggest issues for grounded coplanar waveguide. Now, at lower frequency, this may not be an issue, but at millimeter wave frequency, I've seen this, these first 3 topics be a very problematic issue on numerous occasions. Strip line shown to the right, I'm not going to talk about that a lot. Strip line is not used much at millimeter wave. It is some. And I've given a list of different considerations there. And then finally, SIW to the far right actually has a short list of concerns, but the number 1 concern is the plated through-hole via location and the tolerance for that location. And in this case, for SIW, that's a very big deal at millimeter wave frequencies, but at lower frequencies, microwave and below, that's really not too much of an issue. So I've seen a lot of SIW circuits at lower frequencies, and then at millimeter wave I've seen a few, but not a lot. And it's mostly because of that number one issue of the via hole location tolerance. With many new millimeter wave applications on the market and many more to come, a lot of RF designers are using grounded coplanar waveguide to deal with some of the issues at millimeter wave. And grounded coplanar waveguide in theory can be used to minimize or completely suppress some spurious modes, can be used to suppress unwanted radiation, can also be used to deal with dispersion, where if it's designed correctly you can have minimal or no dispersion for wideband applications. And it also can be used for radiation and minimizing radiation, and that can be an issue at millimeter wave frequencies. Now that's all true in theory, but in practice grounded coplanar waveguide is, or the RF performance for grounded coplanar waveguide is impacted by normal fabrication variations and also material variations. And the next graphic will show that, as well as doing comparisons between microstrip and grounded coplanar waveguide, because this combination is often used at millimeter wave. Shown here is a comparison between microstrip and tightly coupled grounded coplanar waveguide. Microstrip on the left, grounded coplanar waveguide on the right. The field lines are in red, that's electric field lines, current density in blue. And what I'm showing here for microstrip is an insertion loss curve at the bottom, and the first curve, which is gray, that's a microstrip circuit that is using bare copper, so it has no final plated finish. And the next two curves, blue and orange, is ENIG, electrous nickel immersion gold, with thin nickel, blue curve, and thicker nickel, orange curve. Now the thin and thick nickel thicknesses obviously do impact insertion loss, and these are typical ranges to expect for one circuit to another and normal variation as you build circuits on high volume. So you can get this difference in thickness of the nickel. And you can see that it impacts grounded coplanar waveguide much more than it does microstrip. And on grounded coplanar waveguide on the right chart, you can see that the bare copper losses are about equivalent to microstrip, but when you start looking at the effects of ENIG, the blue curve and the green curve, blue curve is the thick nickel, green curve is the thicker nickel, you can see the grounded coplanar waveguide is impacted, the RF performance is impacted much more by ENIG. And that's really due to the ENIG being in 4 areas of the coupled feature, ground, signal, ground on the top copper layer, whereas microstrip is just affected by an edge effect. The left and right edges of a microstrip signal conductor has high current density, and it's there where the ENIG can cause differences in conductor losses. Shown here is the same design basically. It is a tightly coupled grounded coplanar waveguide, and the difference I'm showing is due to copper thickness. And in building a circuit that is using plated through-hole technology, the copper is plated up and the thickness can vary from one circuit to another. Actually, the copper thickness will vary from one circuit to another if you're building these circuits in large volume. Now, of course, you need to talk to the circuit fabricator to understand how much that can vary. But what I'm showing here, the blue field lines are the electric fields. And you can see that in the case of the circuit with the thicker copper, there's more fields in air, and air does have a low dielectric constant. It is the lowest, and of course that means the circuit with the thicker copper is going to have a lower effective dielectric constant, and the phase angle is going to be different, phase response would be different in general. And you can stop the video if you'd like and look through the different bullet points here and understand the differences. But just to keep in mind, copper thickness and the variation of copper thickness, which is normal in building a circuit, that can impact the RF performance, and again, that's especially true at millimeter wave frequencies. In the graphic shown here, these are the results of an experiment I did some years ago, and really what I did was I used the same sheet of material for this evaluation. I cut it in half, and one half of the panel went off to have circuits made with thin copper, the other half of the panel went off to have circuits made with thick copper. And the only difference just being thin and thick copper, using the exact same material and the same circuit designs. And the circuit designs were tightly coupled grounded coplanar waveguide and loosely coupled grounded coplanar waveguide. Now on the y-axis, that is the effective dielectric constant, x-axis is frequency, and the reason the range of frequency is given there is that is the range of frequencies where all 4 sets of these circuits had very good return loss and very consistent RF performance. Now the curve with the lowest effective dielectric constant, the red curve, that is the tightly coupled grounded coplanar waveguide with thick copper. And why that's the lowest curve is because it's tightly coupled, which means there's more fields and air. Air is a low dielectric constant, and with the thicker copper, the sidewalls of the coupled conductors are taller, and you have, again, more air influencing the fields. So that is the lowest effective dielectric constant. And then the next one up, the blue curve, a little higher effective dielectric constant. That's the same design, tightly coupled grounded coplanar waveguide, except thin copper. And thin copper means there's less fields and air, and you can see that by having a higher effective dielectric constant. And then the purple curve and the green curve are the loosely coupled grounded coplanar waveguide designs. Thicker copper is a little bit lower effective dielectric constant than thicker copper, which is the green curve. Now you can see there's a difference of about 0.3 in effective dielectric constant, and remember this is using the same sheet of material, so this difference of 0.3 is really related to the design of the grounded coplanar waveguide being loosely or tightly coupled and thin and thick copper. Now for millimeter wave applications, the control of etching is very important. That's also true for a microwave, but generally speaking, a millimeter wave where the substrates are thinner and the conductor widths are more narrow, how well that conductor is controlled for width and the spacing around that is very important. And we'll look at this on the next couple of slides and see some comparisons between a very common test structure, which is a microstrip circuit that is a series fed patch antenna, and look at differences due to conductor width changing in a range that is normal for building circuits. Shown here is a test vehicle that we often use at Rogers, and it is a microstrip circuit with a ground plane on the bottom that is not shown and the signal plane on top, which is being shown. And in this case you can see narrow conductors, wide conductors, narrow conductors. It's kind of a stepped impedance type of setup, and it's called a microstrip series fed patch antenna. Now what's interesting is the design, this design and most designs actually for this type of structure shows sharp corners on the inside or the outside of these corners is 90-degree sharp corners. That's the design, and that's how the modeling is done typically. However, if you actually look at a circuit that's built with the same design, you do not get sharp corners, and I'm showing that zoomed in a little closer. You actually get a radius there, and at lower frequencies that radius, as opposed to a square sharp corner, really isn't going to make much difference. At millimeter wave though, that radius can make a difference. So this is a topic that you need to talk to your circuit fabricator and understand how much that radius can be and how much it can vary, and try to account for that in your RF simulations, or you could actually design your RF circuit to have those radiuses built into it and then do some sensitivity type of evaluations to understand the variation of that radius, as the circuit fabricator would tell you how much that could vary. As previously discussed, the etching tolerance is very important, and again at millimeter wave frequencies even more so. And here we're showing our test vehicle, which again is a microstrip series fed patch antenna, and we did some models to understand how much a width change can impact the performance of the antenna. In this case, we put a tolerance in of plus or minus 0.6 mils for the width of these conductors, and what we found was we get a frequency shift of plus or minus 550 megahertz, or a range of 1.1 gigahertz, and that's a pretty significant range for a radar operating at 77 gigahertz. Now in this case the gain variation was less than 0.2 dB, which really isn't that significant. However, with certain designs, if you repeat the same type of testing or evaluation, you will find actually the gain can be affected a good amount. So it really strongly depends on the design of the antenna itself. In summary, I've shown several different variables that are normal variables in building a circuit that can impact RF performance. Now these variables can be copper plating thickness variation, can be trapezoidal effects, could be plating. There's several different things, and these are different items that you really should talk to your circuit fabricator about to understand to what degree these different variables can actually alter the performance of the circuit itself. And you should also talk to your material supplier to understand what kind of variation is normal for some of the properties of the materials. This now concludes this session of Coonrod's Corner. Thank you for watching.
For additional information and technical tools, if you're not already a member, join the Rogers Technical Support Hub and gain access to calculators, technical papers, and more Rogers Corporation informational videos. Rogers Technical Information is also available at your fingertips with the Rog mobile app, available for the iPhone, iPad, and Android devices. Check it out today.